Um, this is pretty scary for me. There's a bunch of different technology that has to work in order for this to go. And hopefully the echo is now gone. Apologies for the people hearing that. There's a lot of technology that has to work for this to go, and hopefully we don't have any giant train wrecks. Some logistics, I'm doing all of this from a Jupyter notebook. The notebook is in GitHub. The URL is here. It's also in the notes in YouTube. The environment has connected to it. There's an environment.yml file. So if you're using Jupyter, if you're using Conda, it's really easy to create the new environment. It is important. So one thing I noticed when getting this all set up is in order to make the IPy cytoscape views that I'm going to show when I show the scaffold tree work, in order to have those work, you need to actually configure the widgets NB extension. The command is shown here. That only seems to only happen if you create the environment from the environment.yaml file. If you install IPy cytoscape directly from Conda, you don't need to do that. If you have questions, please ask them in the YouTube live chat. I'm going to try and keep an eye on that while I'm doing this, and I will answer questions as we go along. And if you have feedback or suggestions about this live stream or about the RDKit in general, the best places to do that are the mailing list or the discourse group, and there's a link to the discourse group here. Obviously, you can also provide feedback on the live stream if you want. You can do that just in YouTube. So let's get started. What I'm going to do is show some of the new stuff in the 2020-09 release. This is not an exhaustive list. It's just some examples, some things that I think are highlights or important. If you want a complete list, look at the release notes. That's always a complete list of the stuff that's new and the bugs that were fixed as part of a particular RDKit release. I am also, this says 2020-09. I'll also mention some of the stuff that was in 2020-03, just if I think it's important or if it connects to some of the 2020-09 stuff. First thing to mention are 3 Google Summer Code projects. The first one is the RDKit MongoDB integration. This is actually not in the RDKit itself. It's a separate GitHub repo linked here. It's part of the RDKit organization. This allows you to use molecules and Mongo. So you can do exact structure, substructure, and similarity searches, and it also includes code showing you how to integrate descriptor calculations into Mongo. The next one is part of the RDKit, and this is part of the release, the 2020-09 release, which is the generalized file reader and a multi-threaded multiplier. The generalized file reader makes it easy to read files from or molecules from CSV files or from SD files without you having to worry about the format of the file. And I apologize, I don't have any examples of that in this notebook. I'll do a blog post or something on that later. And then the multi-threaded multiplier allows you to read from a file in a multi-threaded manner, so constructing multiple molecules at the same time, which for some use cases can really speed things up on multi-core machines. Again, I don't have examples of that in this notebook. I'll do a blog post about that in the not too distant future. The last piece is RDKit, an RDKit implementation of the ANI force field. This is a neural network force field for doing geometry optimizations and energy calculations. That is not yet merged into the RDKit itself. There's still a pull request open on this, and I hope we'll have a version of that available in a future RDKit release. There were a lot of code changes with this, and there's still some stuff going on in the review. There have been a lot of changes to the documentation, which is important for those of you that actually want to learn how to use the code. So the cookbook was completely rewritten by Vin Scalfani. That was done as part of the 2020-03 release, and that continues to progress as the RDKit progresses. We're continuously adding new cookbook recipes. An important thing for me is that the RDKit documentation has always had tests associated with the stuff in the documentation. So if you see sample code in the documentation with sample output, that's actually a test. And we have added running those tests now as part of the standard CI build. So we will detect problems with the documentation immediately instead of picking it up shortly before the release, which is what used to happen. And then finally, two other just important pieces of documentation are which pieces of CX files are supported, and then a explanation of the smarts extensions, as well as a documentation of the bits of smarts that are supported in the RDKit. And these are all part of the standard documentation. Okay, let's go and look at some actual new features. The first is we added actually a year ago, so in the 2019-09 release, some simplified JavaScript bindings, which allows you to use the RDKit from inside of JavaScript. Those have continued to expand, and there were some fairly substantial additions to that as part of the most recent release. I'm going to demo this a little bit later when I talk about the Moldral 2D improvements, but I just want to mention it here, and there are links in the notebook, which you all have. So let's go on and look at some stuff in Python, or that's available from Python. I'm going to do the usual thing here in the notebook. I will import some RDKit code. The first thing I want to talk about is version 3 of ETKDG. This is the RDKit's confirmation generator. ETKDG is, let's see, experimental torsions with knowledge, and DG is distance geometry. This is the third iteration of that approach, or of that algorithm. This was originally developed by Sarina Reniker when she was doing a postdoc together with me when I was still at Novartis. She's now moved on to the ETH and continues to work on the ETKDG. The most recent release of V3 includes better handling of ring conformers, which I'm going to demo here, as well as better support for handling macro cycles, which I'm not going to demo here, but there's a link here in the cookbook to a entry from Shuje. Shuje is the one who actually did the work on the macro cycle code. That's in the cookbook. You can see there how the new macrocycle code works. Here's a quick demonstration of the improvements for ring conformers. So I'm going to create a molecule from smiles. I'm going to add hydrogens to that. You always should do that before you generate conformations. I'm going to use initially, just for comparison, I'm going to show what you get from the previous version of ETKDG, so version 2. I will use a random seed so we get reproducible results. Embed the molecule, this gives me conformations. And then because I've set IPython console IPy3D equals true, when I display the molecule on Jupyter, it will show me a 3D structure. This is done using David Coe's 3dmol.js, which is a fantastic library. The integration with Jupyter is really quite nice. What you can see is the ring conformer here isn't really what you might hope. This is, let's see, maybe a twist boat. It's not a clean ring conformation. And the idea for the changes that Sarina made are to make it so that you can get clean ring conformations. Here's how you do that. We're going to use ETKDG version 3, the same molecule we had before. In the parameters, this time I'm going to tell it to use small ring torsions. This is what cleans up the rings. Embed the molecule, take a look at it, and here's what we get. You can now see I'm getting a nice clean chair conformation for the ring. And this in general, including these small ring torsions, will pretty much always give you clean ring conformations. So that's the improvements to ETKDG. Again, if you want to look at what you can do with macro cycles, take a look at Shuje's example in the cookbook. The next example is also something from 2020-03. This is an implementation of the Scaffold Network. We did an application note on that. The link is here. This is work that Nick Stiefel at Novartis sponsored me to do. There's a new module for this, RD Scaffold Network. I'm going to do, for my example, kind of a classic one, and it's from the original Scaffold Tree, Scaffold Network paper, which is a set of antibiotics. So here, these are my 4 antibiotics. And now I'm going to generate a scaffold network and display it. And I'm displaying it using IPyCytoscape, which is just a nice way to view these things in Jupyter. The code for this, I did a blog post on this, which is linked from the notebook. The version that's in this notebook is somewhat adapted from the one in my notebook, and the one in my notebook is adapted from some code that Penn did in a blog post earlier in the year. So he's the one who figured out all the hard stuff. I did a little bit of tweaking, and the results I'll show you down here. So this is for the 4 molecules in that set. This is the scaffold network. This is a little bit confusing with all 4 molecules at once. And so what I did is I put together an interactive widget for Jupyter that allows you to pick an individual molecule at a time. So let's look at the first molecule. And you can see here what you get for the scaffold network for the this first molecule. And this is with the default parameters. So you can see we go from the molecule that gets pruned. So all the side chains get cleaved off to yield the first entry in the scaffold network. And then this is cleaved to give these 2 entries in the scaffold network. So you can see the bond that it's actually cleaving along 2 bonds. So there's one here and then the one here. So this is the default behavior of the scaffold network. I made the interactive widget. I set it up so that you can see some of the other options. You can see what the options do. So by default, we're not including generic scaffolds, but these can also be quite useful. So what you can see here is when I turn on generic scaffolds, each of the scaffolds is generated. There's also a completely generic version of that that's generated, or a version where all of the atoms are turned into dummy atoms. I can further make things further generic by including generic bond scaffolds. And now each of the generic scaffolds is further converted into a framework by just going to converting all the bonds to single. So that's one set of parameters for scaffold network. The other thing that we can do with this is change whether or not we include attachment points. So by default, you can see the scaffolds are shown with the attachment points, so where they were attached to the molecule. Sometimes you don't want that, so you can turn those off. So here now I have the molecule or the scaffold with the attachment point, or this, and also the scaffold without the attachment point. If you don't want the attachment points at all, you can turn those off as well and just get the scaffolds, the bare scaffolds. And again, of course, you can combine this together with the generic scaffolds. And you can see by turning on everything, you end up with a huge amount of output, but you have a lot of flexibility in terms of what you get out of the code. So there's already been a nice paper on this from Nick and Francisca, who was a postdoc working with Nick, looking at using this code and then some retrospective analysis into Kemble to identify likely chemical cores or likely chemical scaffolds in large sets of molecules. So not just this full analysis, but actually going in and picking out the thing that's likely to be was likely to have been the scaffold in the MedChem paper. Okay, next thing to demo is just a small feature, but this is something that I think is really useful for people who are doing training neural networks based on smiles and want to do data augmentation. So one thing people frequently want to do there is take the same molecule and provide it to the network in the training set in multiple ways. And there were hacks that people were doing before, trying to route the smiles at various points, but in the end, you could never really get a good comprehensive exploration of the possible smile space. And we updated that by adding this function mul to random smiles vect. What this does is for a given molecule, it gives you back 5 random smiles. So these are obviously not canonical. They start at different atoms in the molecule, and each time they come to a branching point, they make a random choice as to which direction to go in. So by doing this, you really get a very good exploration of the possible set of smiles for a molecule. You probably wouldn't ever want to use this except for training a learning algorithm. It is important to mention this is random, so if I call it twice, I get different results. But if you want reproducible results, you can provide a random seed. So here's an example where I'm providing a random seed. I get a particular set of smiles, and if I call the same thing again, I get the same results. So Again, mold a random smiles vect is useful for people doing data augmentation for training machine learning algorithms. I can't really think of another useful piece for this. This is a bit of a detail, but is important for people doing reactions. The way that chirality handling and reactions is handled has been improved a lot. So let's look at this. The first thing I'm going to do is construct a reaction from smarts. What we have here, actually, let me just see what the reaction looks like. What we have is a three substituted, what's in this, the reaction smarts is a carbon with three substituents and having a fourth substituent added to it. So you can see carbon 1 connected to carbon 2. There is stereochemistry indicated here. So it's C at, and it goes to C at. The ordering of the substituents on the output change. So we've added, sorry, the bromine has been turned, oh man, I'm confused now. Interesting. Okay. Anyway, I'm going to skip over that because I obviously didn't spend enough time looking at this before I did the demo. The thing is, we've improved the reaction handling so that now there were problems previously. There were problems previously when you did this, it would invert the stereochemistry but do it improperly. And basically now it's doing the right thing. You can go through and look at these examples and convince yourself that that's true. Again, I'm not going to spend a lot of time getting this because, as I just conclusively demonstrated, I haven't spent enough time looking at it in advance. Another reaction relevant piece is deprotections. So this was something that Brian and Joanne at Relay added for the 2020-09 release. Joanne talked about this at the UGM. She did a lightning talk about this that you can also take a look at, but I'll just do a quick overview. The idea here is you can take molecules which have protected functionality, and by just calling deprotect on the molecule, you can have the protecting groups removed. So you see I start here, and I can deprotect simultaneously in one call. I can deprotect both the alcohol and the amine here using these two standard protecting groups. I can also ask the molecule to tell me after I've deprotected it. I can ask the molecule which deprotections were applied. So in this particular case, this deprotected molecule has a property called deprotections, which has the names of the two deprotections that were used. And you can see it here. We've removed a TMS and we've removed a BOC from the molecule. So those are the two deprotections that were applied. The library will give you the full list of deprotections that are available. So these are the ones that are available by default. You can add your own if you like, of course, but this is just a standard set that's provided as part of the distribution. And if you don't want to remove all the protecting groups at once, you can also limit the set that's applied. So in this case, what I'm going to do is take the original molecule we had, and I want to only deprotect amines. So what I do is I just do a list comprehension over all of the deprotections, and I only keep the ones where the deprotection class is amine. So the carbonyl deprotection and the alcohol deprotections are removed from that. And then when I apply that to the molecule, giving this the list of deprotections with only amines, you can see it does in fact no longer deprotect the alcohol, but the amines are deprotected. Okay, Molddraw 2D improvements. This is a big one. There was also a presentation about this at the UGM. So Ed and Dave talked about this. Dave is the one who did most of the work, or a lot of the work that I'll show you. I'll try and be clear as I go who did what work. And Dave and the guys at Ed and the guys at MedChemica funded the work from Dave. And that was in the presentation. Again, that's online and also on YouTube if you want to take a look at it. What I'm showing are things that were added for the last release and for the 09 release, so 03 and 09. The molecule that I'm going to use is shown here. So I picked kind of a random molecule. It's not even a real molecule. It has a dummy feature, as you can see. That's the question mark here. This has, in addition to a few chiral centers, I've also read it in from CX Smiles, and so I've included some extended stereo information. And I did that because with a reason, I did it for a reason. Some of the new drawing capabilities that have been added allow you to show extended stereo. So I wanted to be able to demonstrate that. So this is our silly molecule. Again, I'm going to do an interactive widget in order to show, in order to demonstrate the various options and what they do. So here's our molecule with a particular set of settings. And now I can go through and change. So the first one is, the first option is for the interactive piece is whether it's using SVG or PNG to show the molecule. And so I can turn off SVG and then it's using a PNG. And a thing that you will notice when I do this is it doesn't make much of a difference. And this is a big change relative, this is for the 09 release, this is a big change relative to the 03 release. One of the things that Dave added as part of this most recent release cycle is free type support. And by adding free type support to handle the fonts, we lose the giant problems we used to have with trying to get the fonts to look the same and the text to line up in a detailed way, exactly the same across all the renderings. So the way that the text looks has gotten a lot better, and now it's gotten consistent across SVG and PNG. There's some other options that have been added, so I can add atom indices, and you can see now it's annotating it by the atom indices. This is just a drawing option now. It used to be some work to do that, so there's a drawing option to add atom indices. There's another one to add bond indices, so let's look at that. Let me turn the atom indices off, otherwise it's just too crowded. But you can see now I'm numbering the bonds. This makes it easy, both atom indices and bond indices just makes it easy to track down interesting parts of the molecule that you're interested in, or if there's a particular problem with the molecule, it makes it simpler to check it down. I can also add stereo annotations. So this adds RNS labels when appropriate, or for enhanced stereo, it adds, or extended stereo, it adds the extended stereo labels. So for example, what you can see is this chiral center is S. These two are part of the AND1 group. We provided that in the CX Miles on input, and the double bond over here is E. And so when you select this, it's not selected by default, but when you select this, it shows the appropriate zip labels for all stereo centers that the RDKit recognizes and all double bonds that the RDKit recognizes, as well as enhanced stereo. A couple other changes, you can turn on explicit methyl groups if you like that. So terminal groups are methyl groups are always terminal, but methyl groups, you see the H's on them. You can change dummy atoms instead of showing them with a question mark. You can make them attachment points, so you get this squiggly line. I'm indicating that it's this is useful for showing R groups. And then there's a simple black and white mode that allows you to turn off the colors, so you just get black and white rendering. And of course, you have control over the fonts that are used. You can change the legend. The other thing that's new is you can't do this inside of this demo. If you have a carriage return in your legend, it will now show up over 2 lines. I'll show this somewhere later. That's capabilities or an exploration of some of the options that are available in the renderer itself. You have a lot more control if you want to have more control. You can actually change the font. You can provide your own free type file if you want to. Because it's almost mandatory that I do so at some point, I will do a blog post or an example showing molecules drawn with Comic Sans, just because you just have to do it. Okay, another thing that's new in the most recent release is something I'm actually pretty excited about because I think it's very cool. And that is storing molecule metadata in PNG files. So now, by default, if you create a PNG from inside the RDKit, so either in Jupyter or by using this MoldDraw 2D Cairo class explicitly, you get a PNG. That PNG includes information that allows you to reconstruct the molecule itself. And you can do that with this new function, chem.mol from PNG string. This is the PNG string, it's just the data for the PNG. It will look in the PNG file, and if there is the appropriate metadata, it will give you back a molecule. It'll construct a molecule from that. So I'm just demoing that here. This was the molecule that I started with. It's that same silly one we've been looking at. I convert it to a PNG by doing a MoldDraw 2D Cairo object, drawing the molecule, and then getting the drawing text. That drawing text I then parse with the mol from PNG string, and you can see that I get a molecule back. Here's the new mol, it's the same as the old mol. This is the CX miles that corresponds to that. So the molecule is in the PNG file along with its coordinates. You get exactly the same coordinates you started with. You can also do this with multiple molecules. So if you do draw molecules instead of draw molecule, you end up with all of the molecules in the PNG file. So here's the 4 molecules. These are the 4 antibiotics we were looking at before. Now I call moles from PNG string instead of mol from PNG string, and I get back those 4 molecules, which I'm showing you here. So the reason I think that this is cool is now if you have a PNG file that you generate from the RDKit, like in Jupyter or whatever, and you paste that into a document, your document contains not just a picture of the molecule, but it also contains the data about the molecule, so you can reconstruct the molecule later from that data. Those of you who've been following the RDKit for a while, we added a similar feature for SVG where you could add metadata to SVGs to allow you to reconstruct the molecules. That I ended up being less enthusiastic about because it turned out if you pasted that SVG into Microsoft Word or Microsoft PowerPoint, it would strip all the metadata out. So Microsoft in their infinite wisdom would strip out the metadata, perfectly legal metadata, but they would strip out the metadata that they didn't understand. And so you'd have this SVG that had information about your molecule, but as soon as you put it into a document, the metadata would get lost, which was frustrating. That does not happen with these PNGs. So if you paste this into PowerPoint or into Word, and then go and look in the zip file that the Word document or the PowerPoint document corresponds to, the PNG that's in there still has the metadata intact. Same thing happens with reactions. So drawings of reactions includes the information about the reactions in them. So again, you can construct the reaction back from the PNG string. And you can even add additional metadata. So you can start to treat a PNG file like an SD file. So you have molecules plus data. And you do that by adding metadata to PNG string, and that takes a dictionary. So you give it a dictionary with strings for keys and strings for values. You can add that metadata to the PNG string. It's still a perfectly legal PNG, so if you open it in any image viewer, you can see that. But later you can read that with the RDKit, you can read the molecules back out, and you can also get the data back out. For people who care about such things, this data is all embedded in the PNG using PNG's standard metadata approach. So you can actually see all of the data in any metadata, any piece of software that allows you to look at and view PNG metadata. So this stuff is all available. The molecules themselves are present as there's a number of different formats that can be added. You can either add CX miles or you can add mol files, mol blocks, sorry, or RDKit pickles. The first 2, smiles and mol files, are obviously human readable once you get access to the PNG, so it can be used from other software as well. Anyway, I'm pretty excited about that. I think it's cool. I really like the idea that now images of molecules actually contain information, the information required to reconstruct those molecules without having to use some horrible structure picture to molecule converter. The other thing that came connected to Moldro 2D, the other thing that came in the most recent release, and this was also work sponsored by Nick at Novartis, is a pure JavaScript version of Moldro 2D. I've had a demo for a while. I had a demo for a while of RDKitJS, this minimal JavaScript wrapper. Okay, so a question just came up. If the PNG metadata is safe, are there no security concerns? The information that's in the PNG metadata is the metadata required to reconstruct the molecule that's in the image. So if you're showing a picture of a molecule, you're also providing the data to reconstruct that picture. If for whatever reason you feel comfortable sharing a picture of the molecule but not the structure of the molecule, you can turn off the metadata. There's an option in there to turn off writing metadata. It's just enabled by default. So again, if you're sharing a picture of the structure, it will also by default share the structure, but you can turn that off if you like. Hopefully that was what, Alan, hopefully that was what you meant by is it safe? Are there no security concerns? Feel free to ask a clarifying question if I got that wrong. Okay, back to RDKitJS. This is a minimal wrapper around the RDKit. The intention is not to provide the full capabilities of the RDKit. The idea here really is to have a fairly minimal subset, but something that's still quite useful from within JavaScript. And so this demo file that is linked from the notebook, but I've also shared this link before. This demo file shows how it all works, and it shows most of the capabilities. I'm going to focus on rendering, and I'm going to show two things. I'm going to show the JavaScript canvas, the SVG canvas. So this is an SVG, and this is being drawn with the new rendering code. This is drawing straight into an HTML5 canvas and no SVG required. The demo obviously allows you to type and see the molecules. I can also add smarts to this, so I can find the smarts matches that are present in the molecule and highlight them. You can see the SVG and the HTML5 look the same. We can turn on atom indices. We can turn on bond indices. We can add stereo annotation. There's not a stereo center in here, so it's not showing anything. And the explicit method flag is there. All of the stuff that you would expect to be able to control are available. I'll mention the abbreviations in a moment. But this is just a quick demo of what's possible there. There's very little documentation around RDKitJS. I have created a sample page for doing this. Again, this is also shared in a notebook. I've created a sample page that shows some basics of using the code. So this just has a series of code samples, and when you click them, it runs and shows the output next door. So we can calculate descriptors, we can draw molecules, we can change the code that's there and redraw the molecule. That actually didn't work, which is interesting. Try changing here. Do the same thing with HTML5, and you can see now I got a different output. Okay, that's working up top. It's not working. I think this is probably a bug in my, this is probably a bug in my ability to work with HTML and JavaScript. So a thing that's important to remember with all of these sample stuff and the documentation for RDKitJS, I wrote most of this, and I'm not a JavaScript person, nor am I a HTML person. So it is certainly possible that there are bugs in this sample code. If you find something and can fix it, please let me know. If you can make this stuff look better, or if it appalls you how it looks and you want to make it look better, please submit a pull request. This code is all in GitHub. It would be, I think, be a nice service to the community to have this looking better than it currently looks. But again, the demo's here. It shows you what you can do with the code. Okay, let me go back. Okay, Alan asked a clarifying question. He was wondering if someone can add nefarious metadata to the PNG and try and parse it into the RDKit and if it would break something. If they put bad metadata into the PNG. So something that says it's a mol file but isn't, it's parsed the exact same way normal mol blocks are parsed in the RDKit. So if it were possible to do a SQL injection-like approach via mol file, then the same thing would work via PNG file. Um, there, I'm not aware of any problems like that with the RDKit. That's not to say that they're not there. There almost certainly are. There could be problems like that. Some of these are turning up as auto-fuzzing testing is being done on the RDKit, and we fix bugs that come out of that. But nothing that's come out of that to this point has been a serious security problem. But it is, I don't want to completely dismiss the possibility. The PNGs, this PNG approach doesn't add any additional exposure, right? Because the code that's in the PNG is parsed exactly the same way, using exactly the same parser as the current file formats. So it doesn't add a new vulnerability. A last example, back to the drawing, a last example, and this is really just to demonstrate what you can do with the new drawing code because I think it looks really nice. This is a set of CDK2 or molecules that have been measured against CDK2. I did an R group decomposition and then highlighted the R groups, just color highlighted each of the R groups by which R group it is. What this is demonstrating, and there's a blog post about this, I'm not showing sample code because there's way too much code, but what this is demonstrating is first of all that you can do multiple highlighting now, and you can do stuff like, you notice that I have the whole ring highlighted here and not just the bonds in the ring. That was not previously possible. So this shows some new stuff. That blog post also shows how to do the R group decomposition and then draw the molecules so that they're all aligned the same way. You notice here the molecules are all, the core is oriented in the same way in every image, and I know what the individual R groups are, and that's all shown in the blog post. Okay, that's it for the drawing code for the moment. The next thing I wanted to show is abbreviations. This is another piece of code that Nick sponsored. So again, thanks to Nick. This is something just to help clean up molecule drawings, really. But it also, I mean, in molecule drawings in the RDKit, but also in other pieces of software. So what this basically allows you to do is take molecules. Here's an example molecule, and replace common functional groups with abbreviations for that. So you can see the methoxy has been replaced with OME, and the carboxy has been replaced with COO minus. That's using this condensed mol abbreviations function. This takes the list of abbreviations that you want to use as you're working with it. So that's important. The default abbreviations include a number of common functional groups. You can expand this list if you want to. It's a very simple text format that presents the functional groups and the labels for them. That's basically what the abbreviations code does. And there's a little bit of subtlety to this. So if an abbreviation covers more than 40% of the molecule, it won't be applied by default. That way you don't end up taking a molecule and basically having the whole molecule go away and just become abbreviations unless you want it. So here's an example with a relatively simple molecule. The default behavior is this CF3 is not replaced with an abbreviation because it covers more than 40% of the molecule. But I can specify provide this optional max coverage parameter to condense small abbreviations, and then it will be substituted. So by setting max coverage to 0.8, it will substitute in abbreviations that cover up to 80% of the molecule. Okay, we can also, instead of actually modifying the molecule, we can also just attach an S group to the molecule. So this is with, instead of condense mol abbreviations, it's label mol abbreviations. And again, this takes the molecule, the abbreviations we want to do, and an optional max coverage argument. And then what it does is, I'm demonstrating this by just showing you what the V3000 mol block for this looks like, but you can see it has added a abbreviation S group or a superatom S group that includes the atoms that are the CF3 along with that label. So if you now read this into Marvin Sketch or into BioVia Draw, you'll see the molecule with the CF3 replaced instead of the carbon and the 3 fluorines. It'll show you, those will both by default show you just CF3, but the information about the carbon and the 3 fluorines is still there. On the RDKit side, that does not affect how the molecule is rendered because the RDKit molecule render draws the atoms that are present. So if we want to take a molecule that has specified S groups on it, these specified abbreviation groups, we can call condense abbreviation substance groups on the molecule, and then it will replace that CF3, give you a new molecule back where the CF3 has actually been replaced by the abbreviation CF3. So where the carbon and the 3 fluorines has been replaced by the abbreviation CF3. This obviously works with any superatoms. So if the superatoms were defined using Marvin or using ChemDraw or using BioVia Draw, the same thing will happen. So if you have superatoms in your input molecule that you read in from those drawing programs or from another piece of software, condense abbreviation substance groups is how you get those condensed down so that you can display the molecule with just the abbreviation shown. Good. That's abbreviations. Again, thanks to Nick for funding the development of that. Next are some improvements to the CoreGen integration. For people who don't know that, CoreGen is a piece of software for doing 2D, generating 2D coordinates for molecules. It was developed at Schrodinger and has been open sourced since then. It is much better than the RDKit's default coordinate generation, the code that we wrote. It is also slower, considerably slower for some molecules, which is why it's not the default. But let me show you, we made it a little bit faster in the most recent, or considerably faster in the most recent release. I'll show you how we did that, and I'll show you how to use CoreGen instead of the RDKit's generator if you want to. So I'm going to start with cyclosporin. Macrocycles with the RDKit default coordinate generation. This is kind of the classic pathology. You get a nice circle with some of the side chains sticking off. This is how the RDKit does it. This is the way to draw a macrocycle and know that you're not going to fail, right? You always get something. It's not good, but it's something. We can use CoreGen instead. So a way to do that is to call, once you've imported the CoreGen module, just to call add coords and give it a molecule. And now the conformation that's present is a much better one. You can see CoreGen does a much better job on macrocycles than RDKit does. It also does a much better job on natural products. I mentioned that CoreGen is reasonably slow because it does a lot of work in order to make this happen. So we sped it up in the most recent release by changing the precision that it uses to clean structures up. I'm not going to get into detail on this. You have the notebook. You can look at the timing results. But basically, we made a minor tweak so that we're using a coarser refinement parameters, and it speeds things up. So for cyclosporin, it goes from 160 before to 90 now, 160 milliseconds to 90 milliseconds. And the quality of the output, this is the new output with the bad precision. You can see it looks not terribly different from the new output with the original good precision. This is a macrocycle where the example is more extreme. This takes 156 milliseconds now, so almost 0.2 of a second. You can see the depiction is not terrible. It's pretty good. If I go back to the original CoreGen precision, it now takes almost 3/4, it takes more than 3/4 of a second. And the rendering is a bit better than what we had before, but I don't think this is terrible, and I'd much rather wait 0.16 seconds rather than 3/4 of a second. Anyway, those are there. It's easy to turn on CoreGen generation within the RDKit if you want to use it by default. It's not, but it is not enabled by default because again, there are still cases where things are just rather slow. So you could, if it's important to you to have really good drawings, you can turn it on. We also added one new piece of functionality, which is you can use the CoreGen minimizer. So in this case, if we take a molecule, I just took a molecule here and I drew it badly intentionally. I did this by hand. If I use CoreGen normally, it changes the whole drawing, right? It completely redraws the structure. I can turn on minimize only though. So there's a minimize only setting in the CoreGen parameters. And if I do that, you can see it just cleans up the structure and gives me something that looks better than what I started with. This doesn't always work. Sometimes it will redraw the whole, ends up redrawing the whole structure, but it's just a nice way to do a quick structure cleanup. Okay, that's that. Next, a couple Tautomer related things. The RDKit has had for a couple of releases, actually for a couple of years, it's had Tautomer enumeration, but it's never been exposed to Python. This enumeration was added as part of the MolVS work when MolVS was ported to the RDKit by Susan Leung a few years ago as part of a Google Summer of Code project. We did some tweaking to that as part of the 2020-03 release cycle and added Tautomer canonicalization because that's the thing that always comes up, and then actually released it and made it available in Python. Here's an example of how that works. So I create a Tautomer Enumerator object. This is the molecule I'm going to start with. I can then enumerate all the Tautomers with that using the Tautomer Enumerator object. That gives me back all of the Tautomers that it finds. So this particular molecule has 4 Tautomers. At this point, it hasn't said anything about which of these is canonical. It's just giving me all the Tautomers that it can generate for that molecule using the Tautomer generation rules that are built in. We can, however, ask the code to give us a canonical Tautomer. A super important caveat about this is that this canonical Tautomer is not the most stable Tautomer. It's not saying anything about that. It's just intended to be canonical. So if I give you different Tautomers of the same molecule, you will always get the same canonical Tautomer for them. It's not necessarily the best. It's not necessarily the most stable under any particular set of experimental conditions. It's just intended to be canonical. We put some effort in to try and make it so that it doesn't look horrible, right? That if you're a chemist and you look at it, it doesn't make your eyes burn, but you may think that it's not the best one. It's not supposed to be the best, it's just supposed to be canonical. So for this particular molecule, here's the canonical Tautomer. The Tautomer canonicalization is done using a set of scoring rules, and we can call score Tautomer on each of the Tautomers in order to see what those scores are. So this is an example for those 4 molecules, the scores, so you can get a sense of how the Tautomers are scored relative to each other. But again, canonical Tautomer, it's useful, but you shouldn't, if you look at something and you say, oh, that's not the right Tautomer, you're using the wrong code, right? Canonical Tautomer is not the most stable Tautomer. That's not the intention. Something that was added for the 09 release, connected to Tautomers, this was work done by Gareth Jones. This is something that Schrödinger funded, but it's Tautomer insensitive searching. And this is quite nice. So this allows you to do a substructure search that uses all Tautomers of the query structure. So for my Tautomer query, I'm going to use the same molecule we were using above. So there's my molecule. I'm going to search doravirine for that molecule. You can see that doravirine has a different Tautomer of that 5 ring than the input molecule does. So if I ask doravirine if it matches that molecule, it does not. I can, however, construct a Tautomer query object from that molecule. This allows Tautomer insensitive substructure searching. And now I can ask that Tautomer query if it is a substructure of the molecule. And now you can see, in fact, that it is. So there is a Tautomer of this, which is a substructure of that. I can ask the Tautomer query object to give me back the set of matches. So not just is it a substructure of, but give me the substructure matches. So those are the atom indices. So we could do highlighting with this. And And I can also get back the tautomers of the query that match the molecule. So in this particular case, I say, give me the substructure matches to doravirine, but give me the tautomer that matched it. So you can see I queried with this tautomer, and this is what matched. I can then, if I want to, I can also have get the template molecule. So that's kind of the template which captures all the tautomers. I can have the tautomer query give me that, and I'm just showing that by converting it to smarts because there's not really a sensible way for the RDKit to show you a picture of it. But you can see basically all the bonds involved in tautomerism have been converted into single, double, or aromatic queries. Super important note not to get confused about. This search looks for tautomers of the query, not tautomers of the molecule you're searching in. So here's an example of that. John Mayfield raised this during the UGM. So here's a molecule that I want to use as a tautomer query. I'm going to search in these two molecules for that molecule. And the results that I get back is this molecule does not match either of those. If I use the tautomer query, it doesn't match by default. Initially, it doesn't match either of them, and if I use the Tautomer query functionality, it also does not match either of them. And the reason that's true is I'm not looking at tautomers of the molecule I'm searching for. That I'm searching in. I'm not looking for tautomers of the database molecule. I'm just looking at tautomers of the query molecule. So if you want to handle multiple queries in your database, you need to enumerate, multiple tautomers in your database, you need to enumerate structures in the database. I'm not going to get into details on this. It's in a notebook. There are tautomer insensitive pattern fingerprints that go along with these things that allow you to make the searches efficient. Gareth has done some benchmarking on this, and as long as you generate the fingerprints like what's here, you don't end up with a massive hit in substructure performance and doing tautomer insensitive searching versus tautomer sensitive searching. I'm going to do, again, sometime in the next month or so, I will do a blog post about what's going on with the just query properties. I'm not going to get into details on that here because there's a lot to talk about. There's a lot in this notebook if you want to go through and see what's been done. You can see there's a fairly detailed documentation of the changes that have been made in this notebook. Again, I'll do a blog post on this in the not too distant future. I do, however, want to show the mole enumerator. We just have a few minutes left. So I want to show the enumerator. This is also query stuff, but the idea here is to take mole files that have query features in them and to enumerate some of those features. The stuff that came with the 09 release and with the most recent release is an initial implementation, and we're going to add more of this in the upcoming releases because I think it's really super useful. So the first thing to look at is position variation bonds. So this is a molecule I drew in Marvin where I have indicated that this O-methoxy is connected to either of these any of these three atoms. The RDKit doesn't know how to render this as of the most recent release. You're not seeing that it's connected to those three atoms, but it's these three atoms that it could be connected to. With the mole enumerator object, I can actually say, take that molecule and give me all of the things that it corresponds to. And you can see I get back these three molecules. This looks like hell, right? It doesn't generate new coordinates. It just reattaches the bonds. So if I generate new coordinates for them, you can actually then see that what actually comes out of this is these three molecules, which is what you would expect based on the position variation bond. So this allows you to take that query object with the position variation bond indicated, generate all the possible molecules for it. Those come back as a mole bundle, which you can use for substructure searching. The same thing is there for link nodes. Again, the RDKit doesn't know how to render this yet, but I drew in Marvin a query here where this is a link node, and this can appear between 1 and 4 times. If I enumerate the molecules, you can see this is what comes out. So those are the 1 and 4. molecules that are contained in that mole bundle, which is described by this SD file or mole block. Okay, there's a bit more in the notebook. I'm going to wrap up now because we're at about an hour. There's a bit more in the notebook talking about how what's been done to support enhanced stereo in substructure searching. Again, you have the notebook, you can see what's there. And there's some explanations of what's there for the new stereochemistry code. There's also a presentation about the new stereochemistry code that was done at the UGM. The presentation, the slides for that are linked from the notes in the video, this video. And if you go to the playlists, the YouTube playlist for the RDKit 2020 UGM, you can find the presentation where Ricardo and I talk about what the new stereochemistry code does and how it does now proper SIP labels for molecules, which the previous RDKit releases didn't always do. Okay, I'm going to wrap up with that. I'm happy to take additional questions if there are any additional questions that come up in the live chat. If you want to follow up and have additional questions, again, please send them to the mailing list or post them to the Discord group. I will continue to monitor the comments on this video. So I will, once I shut down the live stream, I will do whatever I need to do with YouTube to get the video saved so that it's there. You can watch it later. And I will also monitor it for a while to answer questions that are asked directly on the video. But if you have questions now, you want to type them in the live chat, I'm happy to go ahead and answer them. Otherwise, I'll wait a couple minutes and then we'll wrap this up. Thank you. I hope that this was useful. If you think a session like this is something good and it's something I ought to do with future releases, please let me know. Again, in the comments here in Discord discourse or on the mailing list. Thanks for attending. Bye-bye.